It's a real pleasure to be here again in Pisa. So the topic I want to talk to you about is, in some sense, a bit of I think of it as a nice application to a lovely question by Umberto Zannier. It sort of illustrates how these more modern methods arising from homotopy theory enable us to now use classical constructions from differential topology to solve algebraic problems. So of course, I'm sure you all know, if you take just the usual n sphere, you can think of this as just sitting inside Rn plus 1 as the summation xi squared equals 1. Then this is a smooth manifold, so it has a tangent bundle. And as I'm sure you all know, is when n is even, so this does not admit a nowhere zero, a continuous, so let's say C infinity or zero section for an even. This so-called, well, in Germany they call it the hedgehog theorem. In the United States it has a somewhat more disgusting name, so I won't refer to that. Yeah. So now how certainly many ways to prove this, but the method from differential topology, so one proof, is okay, you can look at the right, if it did have some section, you take some section, so if this exists, say nowhere, I'll just say non-zero, nowhere zero, there exists such a thing, then you have the theory of the Euler class. So every vector bundle, real vector bundle, has an Euler class, in this case the Euler class of the tangent bundle. It's a rank n bundle, so it would live in Hn on Sn. In general, the Euler class lives in the orientation bundle of the vector bundle. You take the top wedge, and that'll either be a trivial bundle or a Mobius band type bundle. But in this case, the n sphere is, of course, oriented, so it lives in the top cohomology, which is the same as the zeroth homology. And then you have the degree map to the integers. And the Gauss-Bonnet theorem says that the degree of the Euler class of the tangent bundle is the Euler characteristic of Sn, and of course, this is equal to 2 when n is even, and it's 0 for n odd. Well, I mean, even for S0, it's 2. Okay, so on the other hand, if you have a nowhere zero section, of course, in general, if you take a section of a bundle and it vanishes at the right dimension, let's say transverse to the zero section, which is certainly a nowhere zero section is transverse to the zero section, then the degree of the Euler class is just the number of zeros counted with the orientation, plus or minus. So that says this thing has to be 0, which is a little strange because 0 is usually not equal to 2. So okay, so that's a contradiction. So no such gadget exists if n is even. Now if n is odd, there's no contradiction. And in fact, you can quite easily write down a nowhere zero section. Let's just write it down. You can use this equation here. The tangent bundle is, of course, just the perpendicular to the normal bundle under the usual dot product. So you want to find, you can define your section V, x1, xn plus 1, to be the following vector. Let's see if I get this right. I think we can do something like take x2 minus x1, x3, x4, minus x3. And let's see, n is supposed to be odd, so n plus 1 is even, so it ends up n plus 1 minus n. And of course, since the normal vector at the point x is just the vector 2x1, 2xn plus 1, these are perpendicular, and so it gives you a section of the tangent bundle, and when it's 0, then all the x's are 0, but then you can't have this equation. So there you are. There's a nowhere-vanishing section. And of course, it's not a contradiction because the Euler characteristic is 0. All right, very good. And no clocks anywhere. I'm going to keep track of the time. So now, I've already written this down as satisfying an equation. So we can ask the algebraic question. So now let's let K be just some field, and we want to have this equation to give us a manifold in the algebraic sense. So we want to assume that the characteristic is not 2. So now we have our Sn over K sitting inside what we write as the affine space of dimension n plus 1 over K as the solution set or scheme of the equation summation xi squared minus 1. It's a nice object from algebraic geometry, a quadric hypersurface in affine space. And the usual notions from differential topology apply perfectly well here. This thing has every right to be considered a smooth gadget. It has a tangent bundle. So we can ask the same question. Does the tangent bundle of this thing here admit a nowhere zero section? But we already know if K is the real numbers, can't possibly, right? Because, see, the thing about algebraic geometry is the points of this thing are not just the points with coefficients in K. This thing, even when K is the reals, it has complex valued points. You just don't see them over the reals. They're still there. They're just complex solutions to this equation. But if you had a nowhere zero section of the tangent bundle and you're restricted to the real points, well, you wouldn't, it would give you a nowhere zero section. So, at least for n even, this wouldn't be the case if K was the reals. On the other hand, if n was odd, well, this thing is just some algebraic gadget, right? It works just as well over any field, so we get a similar answer. Well, okay, not so interesting. But what about K being the p-adic numbers? So this is the question that Umberto Zannier came to Christopher Denninger and Fabio Morel at various times, and then through it ended up through Christopher Denninger. It didn't end up with me. It then came to me, and through Fabio Morel, it came to Alexey Ananyevskiy, and then Alexey came to visit, and he asked me about this question that Fabienne had asked, and he said, well, that's strange. Christopher Denninger asked me the same question 2 years ago, and I had some ideas but wasn't able to do it, and we got together and, basically answered the question. Okay, so let me tell you how that goes. Maybe I should also say, let's see, if one simple answer, if K is algebraically closed, I just write that here, then the answer is yes. Whether, of course, n is odd, but even if n is even. And so why is that? Well, algebraically closed, you don't even need that. You just need that the square root of -1 is in K. Then the answer is yes, because you can take this equation, it starts out, you just write x1 squared plus x2 squared is equal to, x1 plus ix2 times x1 minus ix2. And you can call this guy, say, z1 and this guy z2. And then, again, you play the same game. You can explicitly write down a section. You can take, now you just take v to be 0. I think you do something like 2x3 and then minus z1. And then you go merrily along x4, x5, minus x4, etc. Do the same thing. And that also, since now you have one less space, that also works with n being even. Okay, so K algebraically closed, like the complex numbers, you get a section. And it turns out, in fact, the same argument, same construction, works as long as this equation has a solution in K. So it's just a matter of diagonalizing a quadratic form. Quadratic form represents 0, then you can always change coordinates so that the first two terms, instead of being an x squared, just, non-trivial. Thank you. Ofer Gaber's not in the audience, but nonetheless, yeah, right. Nonetheless, has a non-trivial solution. So if it has a non-trivial solution, you can rewrite the equation so it starts out, it's equivalent. You can change coordinates. It doesn't really matter. It starts out again as z1, z2 plus the summation ai xi squared. And then a very similar formula to the case we just did gives you a solution. Okay, so for example, you take K to be QP, and P is odd, then the answer is yes. Even so, of course, why is that? Well, it's some standard business about quadratic forms. So you want to know, the first case would be x1 squared plus x2 squared plus x3 squared. If this thing has a non-trivial solution, and of course, if you add any number of more variables, it still has a non-trivial solution. And you know that this thing has non-trivial solution in the field with p elements, because it's a little counting argument that everything in FP is a sum of 2 squares. So -1 is a sum of 2 squares, and then you take this one to be 1, and you're done. All right? But again, for p odd, if you think of this as a family over ZP, it's smooth over ZP, so you can always, Hensel's lemma, you can always lift a solution to something where the derivative is non-zero. That's where we're using the p is odd. The derivatives here are non-zero. You can lift the solution over FP to a solution over ZP. And of course, if you have a solution over ZP, you have a solution over QP. All right, so this is Umberto's question. What about p equals 2. Okay, so I'll tell you the answer. So the answer is it doesn't have a solution for p equals 2. This equation does not have a solution for Q2. However, the tangent bundle for S2, that's what this one is asking about for S3. The tangent bundle for S2 over Q2 does have a nowhere-vanishing section. You can prove that, but we don't have a formula for it. So we were able to prove this by the method here using some kind of Euler characteristic computation, and we can say, well, therefore there must exist a solution by some other theorem, but up to now we don't have a way of writing it down. Well, it's, okay, I should say, for odd dimensions it has a solution. For even dimensions, at least 4, it's easy to show that there are other ways to show that it has a solution. It's rather easy. The critical case was for n equals 2 and p equals 2. Okay, so let me try and explain a little bit about how we got to this rather amusing result. So this is thanks to motivic homotopy theory. Okay, so I'll make I'm going to run out of room here. So let's see. Oh, I guess I'll cheat here. I'll make a dictionary. Oh, this is bad. I'm going to have to use 2 slots for the dictionary. So I think I'm going to just punt, and I'll have to get rid of this. If you don't mind. That'll put it up here. Try this. Okie doke. So what's the dictionary? Here's my dictionary. I'll put differential topology on this side and algebraic geometry. And scary words, motivic homotopy theory. On this side. See what we can do. So let's review the proof. So we've already seen that we have the usual n sphere inside of Rn plus 1. And we already just wrote down the same equation, but in fact, this the proof was for a smooth, think of this as a special case of a smooth quadric hypersurface in affine n plus 1 space over a field K, where we assume characteristic of K is not 2. And so, if you do such a thing, of course, you all know you can take any symmetric bilinear form or quadratic form, characteristic not 2, and diagonalize. So you can assume it looks something like this, AI xi squared equals 1. That's the equation I want to look at. So algebraic is happy with equations. Then here we have the tangent bundle. So then maybe I should call this something, maybe call it Q0, because I'm going to need a Q later on. So then we have the, tangent bundle Q0. And I've mentioned that this thing exists purely algebraically. Good. And then we have the Euler class. That's what we needed. And this lived in Hn, Sn, Z. But in fact, sorry, I should probably just talk about just an arbitrary vector bundle over some smooth manifold of rank R, and this will live in HR on M, and in the local system of the orientation bundle of V. Right? I hope that's okay with you. Either Z or a twisted version of Z by the double cover of the bundle given by the bundle minus the origin. And here we have a similar thing. So now we're going to see something rather new. Again, now we have V, a vector bundle on some smooth variety X, and we have its Euler class. And this lives in the Euler class I'm going to talk about lives in this thing called the Chow-Witt group. R will be the rank of my bundle. It's the Chow-Witt group of X. With the orientation bundle, you take the line bundle, which is just the dual of the determinant bundle. So I'll put a little dual here. So you take the top exterior power of V, that's a line bundle, you take its dual. And you should view this, it's a line bundle. If you have a line bundle on a real manifold, you remove the zero section. It's either two components or one component. That's like an orientation bundle. In the algebraic theory, just an arbitrary line bundle plays the role of an orientation bundle. Okay, we've got that. And then the other thing we needed was we have the degree map. So I'll explain these things. That'll be most of the remainder of the talk. So explaining what these things are. We have the degree map going from the top cohomology. Let's say M has to be compact now. Top cohomology of M, coefficients in its orientation bundle. That's the orientation bundle for the tangent bundle to the integers. For connected M, that's usually an isomorphism, I guess. Okay, and here we have degree map. Degree map. Here, X is going to be X is now smooth, proper, projective. The algebraic version of compact. You're not happy with that? Dimension X equals M. And this is a degree map going from this Chow-Witt group, degree M, twisted by the inverse determinant of the tangent bundle, which is what's called the canonical bundle of X. This, by definition, is you take the tangent bundle, its top exterior power, and its dual. You're not familiar with that. And that goes to, where does it go? It doesn't go to the integers. Now we have a new interesting player, sorry for the blackboard, GW of X, of K, sorry, terrible. So now, I'll say what that is. I'll say what it is, but I'll say a little bit more. GW of K is the Grothendieck-Witt ring of non-degenerate quadratic forms over K. So that's the really interesting thing that the motivic homotopy theory leads you to, is that instead of degrees landing in the integers, they land in the Grothendieck-Witt ring of quadratic forms over the field over which you're discussing your problem. So that's the new information here. All right. And let's see. Is that okay? Everybody happy with that? Right. Let's see. Maybe I should say, this is a little addendum, we have some Poincare duality isomorphism that this guy here is just the same as the H0 with Z coefficients. That's Poincare duality. And the degree map is just a push-forward map on homology. And here, you have similarly a Poincare duality isomorphism. This Chow M tilde thing, this Chow-Witt group, is by Poincare duality. It's just not going to help you too much. It's this thing here. And I'll tell you what this thing is. It has a fairly concrete description. Okay, Grothendieck-Witt ring. Let's see. Then we have the usual Euler characteristic. Euler characteristic of M in the integers. And here we have this motivic Euler characteristic, just to give it a scary name. I'll write it like this. It depends on your base field. And again, instead of living, this is the same theme, instead of living in the integers, it's a quadratic form. Maybe say one word about why is it a quadratic form? If you took k to be the complex number, your x is some variety, you can look at its space, say a manifold of complex valued points, and this Grothendieck-Witt ring always has a rank map. Quadratic form lives on some vector space, and you take the dimension of the vector space that maps to the integers. When you take the rank of this thing, and k happen to be the complex numbers, you're just getting the usual topological Euler characteristic. But if k happened to be, this is in case k happened to be inside or equal to the real numbers, then you also have a signature map to the integers, and this will tell you the Euler characteristic of the real solutions to your equation. So it puts them together in a nice package. Okay, just to give you an idea of the information that might be telling you. All right. And then we have the Gauss-Bonnet theorem, which sort of puts these things together. It says the degree of the Euler class of the tangent bundle on your compact manifold is the Euler characteristic of the manifold. And here we have this motivic version, which says the same thing, that if you take this degree, we have this degree map here, and you have the Euler characteristic of the tangent bundle of your x, right? The tangent bundle, this is the inverse dual the determinant of the tangent bundle, so it lives in exactly the right group we need to take the degree. This is equal to this motivic Euler characteristic, but now this is living in quadratic form. So this is a theorem. This is for x smooth and projective over k. So defined by homogeneous equations in a projective space. That's projective. Okay, and finally, we have sort of a theorem which comes from obstruction theory. I'll just call it obstruction theorem. Obstruction theory, which says that V on M, rank of V equals dimension of M, maybe M should be a compact manifold, then the Euler class of V equals 0 if and only if V admits a nowhere zero section. Okay, and we have the same thing here. This is a theorem of Morel. Maybe I should say the fact that the degree map here lands in here is also due to a theorem of Morel's. So Morel, but that's also kind of helped by a theorem of Asok, Hoywa, and Wendt. And there were a bunch of other people that worked on this, Bob Redekar and Sridharam and Marco Schwisten, but let me just mention these names here explicitly. Now this is a little different. Now this is for x smooth and affine. So remember, affine is something defined by equations in just, the vector space, the affine space over the field, and it's never projective. It's never proper. It's never compact unless it's just a finite set of points. So it's a completely different setup. But in any case, V to X vector bundle rank of V equals dimension of X. then it's the same theorem. The Euler class of V in this Chow-Witt group equals 0 if and only if V admits a nowhere zero section. It's never, no, wherever over the algebraic closure. It's never zero. Any way you wanna, no, just not zero, yeah. Yeah. No, not just a rational point. No. Just, yeah. At every closed point, if you evaluate it at any closed point, it's not zero. That okay? Okay. Good. So, maybe for time? Okay. I have no idea how much time I have left. Want to give me a... Great. Okay. We're in good shape. So maybe I should make some explanations. Okay, so possibly some of you are, let's see, where do we start? Some of you might be familiar with the usual Chow groups. I put this little tilde. There's the Chow groups without the tilde. And this, in some sense, are the algebraic geometer's version of homology or cohomology. So you have the usual Chow groups. These are the codimension Q algebraic cycles on a, we'll say, smooth variety X modulo rational equivalence. And this comes as a presentation. You take the free abelian group on the subvarieties, the integral subvarieties of X. This is integral codimension Q. And the Chow groups are a quotient of this thing. And the things that define the relation are you take, say, W inside of X integral codimension Q minus 1, and you take the rational functions on W, and this is the map which takes a function to its divisor. It's zeros minus its poles. Okay. And the idea is you take some subvariety, it already has no boundary. So there's no boundary map. Like in usual homology, you take, chains that have zero boundary modulo boundary of other chains, right? So these are the chains, but they automatically have zero boundary. And these are the things you're taking, these are the chains of higher dimension you're taking the boundary. That's the idea. So it's kind of like homology or cohomology, and things are smooth. Okay, so that's a fairly familiar thing. And now we want to say, what's this thing with this tilde on it? You basically replace, like we did before, well, there's an extra twist here, which makes things twisty. You have a line bundle. This is orientation line bundle. And you replace the integers with quadratic forms, except the quadratic forms are not forms with values in some field or something. They're forms with values in the fiber of this line bundle, maybe twisted, whatever. It's a slightly twisty version of quadratic form. So this has a presentation. It looks like this. You take the direct sum over Z contained in X, integral codimension Q, and now you take the Grothendieck-Witt ring of quadratic forms over the functions on Z. Remember there's a rank map to Z, so this compares with this, but the values are in, you take the normal bundle of Z in X. Well, Z may not be smooth, but certainly at its general point, it's going to be smooth in X, so this will make some sense. You take this thing, you tensor it with your bundle here, and then you restrict to the general point. That's what this thing means. If you're not too happy with that, don't worry about it. It's quadratic form. Okay? Now there's a boundary map to the same thing. Let's see, W, maybe X, Y's inside of X, codimension Q plus 1, and you have the same thing, except now you use the Witt ring. The Witt ring are quadratic forms modulo the class of the hyperbolic form. The hyperbolic form is form in two variables, h of xy is x squared minus y squared. Notice this thing has rank 2, but signature is 0. Okay? And here, you have a similar thing with a group that I'm not going to explain. Now this thing, if you know, this thing is Milnor K1 of this field. Okay, if you don't know, you don't know. You're not. Thank you. Even better. This is, now it's Milnor K1 of the field, and there's a quadratic refinement of that called Milnor-Witt K1 of the same field. So, if you didn't know what Milnor K1 is, you're not going to know what this thing is, but anyways, it's some quadratic refinement. So this, and you have some kind of divisor map here. So it's like taking the divisor of a function, except there's information from quadratic forms carried along. I'm not going to explain any more than that. So, okay, but now it's not really a presentation. This Chow-Witt group, twisted by L, is just the cohomology here. It's the kernel of del modulo the image at this spot. So you really do have things, these are the chains, or cochains. There's a boundary map here that has to be 0, and then you mod out by boundary of chain of one dimension higher. Good, okay, that's that. Doesn't explain too much, but roughly speaking, the idea is algebraic cycles are sums of subvarieties with integer coefficients. Chow-Witt gadgets are sums of subvarieties with coefficients of quadratic forms in the field of functions of the underlying variety. All right. And these behave much like homology, or they both have the same kind of thing. They have pullback maps. If you have f from x to y, then you have a pullback map going from the Chow-Witt groups of y to the Chow-Witt groups of f. And if f is proper, you have a push-forward map, but maybe I should say something about this push-forward map, because this is where the orientation comes in. The orientation comes in because there's a twist in the orientation. Maybe just the push-forward maps look a little funny. The push-forward map, so let's say f from, how do I write it? From x to y is now proper relative dimension d, and so this goes from Chow-Witt q on x. So you have to have a line bundle L on y now, f star L, but you have to tensor with the orientation sheaf on x. And then it goes to Chow q minus d on y with coefficients in L tensor the orientation sheaf on y. So the push-forward maps have the orientation. Okay, so let me just do a special case. It's the degree map. So the degree map, if you have x smooth and proper over your field, I'll write that this way, let's call the projection map pi, then the degree map, this is just pi lower star, and this is smooth and proper of dimension n. It goes from Chow-Witt groups on x twisted by omega x going to the Chow-Witt groups codimension 0 on k, and this is just, I mean the degree map is supposed to land here, right? If you look at the presentation, you just have things of codimension 0 in the middle and there's nothing else. There's nothing of codimension 1 on a point, and there's nothing of codimension -1 on anything. So that's just what this is. And I just want to say there's a Poincare duality isomorphism with the same thing where you just index by dimension. And this thing just has generators. The direct sum of the Grothendieck-Witt group of the residue fields to closed points. So as Angelo pointed out, if you have a variety over some field, it might, over a field K, it might have points where the coordinates are in K, but it also could have points where the coordinates are in some finite extension of K. Those will be all the closed points. So this residue field here may not be K, it could be some finite extension. Okay, and what's the map? You take, I'll just write over here, I'm not supposed to write. You have your point P inside of X, and this is, of course, mapping to spec K. So P is like spec KP. So what's the map? You have the Grothendieck-Witt ring of KP, should have a map down to the Grothendieck-Witt ring of K, and this is the so-called trace map. So if you have a quadratic form on some vector space, with values in KP, this is some KP vector space. Well, it's also a K vector space, right? Because this map, KP is a finite extension of K. And then you have the usual field trace. Let's assume that this is a separable extension going down to here, and this would be the trace from KP down to K of the quadratic form Q. So that's how this trace map is defined. So it's fairly concrete. Okay, and the theorem is it passes, you have relations in there, and it passes to the relation. Okay, so that's that. Let's see, we're going down our list. We had somewhere we had the Euler characteristic. That's the degree map. We had the Euler characteristic, so let's say something about that. So, how am I doing for time? What have we got? Great. Oh, wow. Never have this much time. Okay, so, Euler characteristic. So this is really fun. Motivic Euler characteristic. So, for those of you who are Alberto's talk, he mentioned this motivic stable homotopy category over a field. So I'm just going to mention that just to scare you all, and then I'll reassure you after that. So don't worry. So if you have X, which is smooth over K, there's some technical things in finite characteristic, but I won't say them. Then you have this object, the infinite P1 suspension spectrum of X living in the motivic stable homotopy category of K, and this is a dualizable object. And if you have a dualizable object, then you can take any endomorphism of it, and it has a trace, and the Euler characteristic here is defined to be the trace of the identity on this guy here. This is just to amaze you later on. Don't worry. And this lives in the endomorphism ring of this funny category of the unit object, which is the motivic sphere spectrum, whatever that is. Who cares? But then you have Morel's theorem, which I alluded to, Morel's theorem, which says that this thing is just the Grothendieck-Witt ring of the field K. So that's why you get this thing in here. Okay, but for X smooth and projective over K, there's a very explicit way of describing this thing. You have the Hodge cohomology. You have the cohomology of X with coefficients in the P forms on X. This is a finite dimensional K vector space. Let's say n is the dimension. And then you have a cup product pairing. This thing pairs with n minus q x omega n minus p x going to hn x omega n. And then Serre duality, or any way you want to say it, is a canonical trace map down to the field K. Okay, so here you have a product, here you have a map to K, and lo and behold, that gives you a quadratic form when you take them all together. So, in other words, and if you take all the cohomology of all the forms together with the trace composed with cup products, call that Q Hodge. This is a quadratic form. This thing represents this. This is, formally speaking, really a virtual quadratic form. I cheated a little bit here, but just to give you the idea, in the Grothendieck-Wigner and the K. So it's a fairly concrete, it's fairly concrete object, and fairly concrete because if someone hands you an algebraic variety and they ask you to write down what this quadratic form is, unless it's a very simple algebraic variety like projective space or Grassmannians or something like that, you're going to be hard pressed to really make this explicit. Okay, but we're in good shape because and in addition, let's see. In addition, we have the Gauss-Bonnet theorem, and we also have that when you take the degree of this gadget here, the degree of the Euler class of the tangent bundle of X is equal to this. So this is motivic Gauss-Bonnet. And these two theorems are theorems due to myself and Arpon-Raxin. Okay, so we're in good shape. You have a fairly explicit expression for this thing, and you have the Gauss-Bonnet theorem. Right. Okay, so one last bit of ingredient we need to make the program work is we have a computation due to myself with Simon Pepin Behalur and Srinivas. So in the interest of time, I won't go through all the details here, but they say if you have X inside of a projective space, defined by X is defined by some homogeneous polynomial of degree D, then there's a certain, you take the Jacobian ring of this F. This is very explicit. This is just you take so this would be polynomials and variables x0 up to xn+1. That's where this F lives. And you don't mod out by F, you mod out by its partials. You have to assume that this is prime to the characteristic of K if that happens to be positive. Okay? So this is the Jacobian ring, and let me just say it, this is a graded ring because these all have degree D-1, the homogeneous degree D-1. This is a graded ring. Certain graded pieces of this give you these Hodge cohomology groups, or at least most of them. The important ones, the so-called primitive Hodge cohomology groups. If you don't know what that is, it doesn't matter. Those are the primitive ones essentially determine what this quadratic form is for a hypersurface. And there's also a particular element in the top degree of this thing. The top degree of this thing is one-dimensional. There's a canonical element found by Shea and Storch, and that defines a quadratic form on this thing. Quadratic form. And then if you restrict it to the part, so let me call that quadratic form restricted. Let me call that something to the quadratic form q jack. That's the quadratic form on here, restricted to the part which gives you the Hodge cohomology. And the theorem with Srinivas and Pepin Lahalur is that this almost gives you the so here's the computation. Is that this Q Hodge is equal to, let me just use this notation here for a minute, plus minus D times Q jack. So this notation, this is the quadratic form, x goes to D times x squared. Okay, so we have, this is all very explicit. So let me give a particular case of interest. If x is equal to this thing here, now I have to make it projective. So let me take the projective closure of the thing we're interested in. You change the 1 to the x0 squared, then the Euler character, plus some multiple, I guess it's, this is for n even. That's the case we're interested in, plus n over 2 times the hyperbolic form. Then this chi of x, this is q, let's call it q now. That's what I wanted to call it. 2 plus, see that's the d is the 2, and then we have minus 2, but the q jack here turns out to be just the product of the coefficients. So 2 times the product of the AIs, plus n over 2 times h. So we know exactly what this Euler characteristic is. So there's one more ingredient, then we can finish off the proof. Okay, so what's the situation? So this thing is not the thing I want to talk about, right? I want to talk about the affine thing. So how do you compare them? Remember I said there's no degree map on the affine thing, but there is a degree map on the projective thing. So we want to study, so what about our Q0, which was the locus of zeros of this thing. Well, this thing is open. This is just what I get by, if you work in projective geometry and you set the x0 not 0, and you can divide by it, and then just becomes, if you think these are sort of big x's and you divide by, you're just setting this thing equal to 1, essentially. So there's an open immersion inside of Q, which was V of this is in the projective space of dimension n plus 1. And what's the complement? Let me call that Q bar. That's when x0 is equal to 0. This is V of summation AI xi squared. Homogeneous in one less variable. So that's inside of Pn. Call that I. And associated to this situation, we have a localization sequence. And it looks like this. So remember, I'm going to invoke this duality, this Poincare duality. We have Chow 0 of Q. It restricts to Chow tilde 0 of Q0. Remember, this is where, after Poincare duality, this is where the Euler class of the tangent bundle is. Okay. And of course, here, this is also smooth. Sorry. Here we have the Euler class of the tangent bundle of Q, and, everything is natural. This maps to this. This is just J star applied to this. And then here we have the error. Okay. And now these things are smooth and projective, so both of these things have a degree map. And that commutes with this push-forward map, because degree is also a push-forward. So this gives us this diagram. And what does this tell us? Well, we want to apply the theorem of Morel, Asok, Poiwa, and Wendt. We want to know when is this Euler class 0. And it would be nice if this degree map is an isomorphism. So let me mention a result of Feld, which, if you translate it, says if this Q has a K rational point, then this degree map is an isomorphism. This degree map here. So let's just assume, which will be the case for our spheres, right? The point 1, 0, 0, 0, 0 is always on the end sphere. Okay, so let's assume, I'm almost done. Then, the Euler class, this thing, is equal to 0 in, whatever child tilde it's supposed to be, if and only if 2 plus 2 times the product of the AIs plus n over 2 times the hyperbolic form is in the image of the degree map applied to child 0 tilde of Q bar. Okay, that's the result. And this is something you can actually compute. So, in fact, there's a refinement of this. So that follows from this. And you can do this, then check this happens for K equals Q2 and N even bigger than or equal to 2. It's an easy check. So I'll just leave it at that as a little exercise for you to do at home. What is? This is true, that this condition, this happens, this thing happens. Thank you. Yeah, thanks for clarifying that. Pardon me? What's the pi? This is a product. Remember I had my coefficients. This was, remember, Q0 was defined by summation AI xi squared equals 1. So it's a product of the coefficients in the quadratic form. In case we're talking about the sphere, that's just 1. And, of course, you know that 2 plus 2 is 1 plus 1 in GW of K. So. Right? You all know that. So let me just conclude. I probably have less than any amount of time. Let me conclude with one. This looks a little hairy to check, but let me just say one more thing, which comes from applying some of the beautiful results from quadratic forms due to Pfister and Knabush and others, mainly in the 60s and 70s, I guess. So, in fact, if Q of K is not empty, then this Euler characteristic here, well, of course, I should say, then we had Morel's theorem, right? Morel, Asok, etc., which says this is equivalent with this thing here admitting a nowhere zero section. I think I said it, but let me just. Okay, anyway. This last condition, then this thing is equal to 0 if and only if the following things happen. So let D equal the set of values of my quadratic form. Okay? And let's let this thing here equal the subgroup of k star modulo k star squared generated by the image of D. Okay, so then this thing is equal to 0 if and only if minus 1 is in D. So this is something you can really get your hand on. And it's easy to check for like Q2 that this is true. So for example, what happens if we take k equal to Q2? Okay, so if you take Z2 cross modulo Z2 cross squared, this is the same as Z mod 8, is the classical thing from p-adic number theory, I guess, cross. And let's see now, what could be in there? If you take 1 squared, we're looking at the quadratic form x1 squared plus x2 squared plus x3 squared. Remember, we want to look at s2. So 1 squared plus 1 squared plus 1 squared is 3, I think. Is that right? And 1 squared plus 2 squared plus 0 squared is 5. So these are both in D, and that means 15 is in this. But 15 modulo 8 is minus 1. There you are. Easy peasy. Okay. But notice I needed 2 values. If my quadric Q bar has a rational point, then I can always do it with just 1 value. And that's why, if it has a rational point, I can find the formula for this section. Here, I need 2 values, and I can't find the formula. Okay, so I'm sure I'm over time, so let me apologize for that, and thank you for your attention. Yeah. Yeah. It all, yeah. Well, they're not smooth. I mean, these things are, I mean, of course you can still find smooth quadrics, but not for the form summation AI xi squared. So, our Jacobian ring business requires the degree to be prime to the characteristic. It really requires that. So, it's all, I mean, even our is, most of that goes way back to, Carlson and Griffiths. I mean, they look at these things to prove Torelli theorems. They relate the Jacobian ring of a hypersurface to the Hodge cohomology. And, their computation has sort of more denominators. We refined it a little bit to get rid of some of the denominators to make it work better in positive characteristics. But even then, the argument really breaks down if the degree is not prime to the characteristic. So I don't even think we weren't able to even show that these graded pieces in the Jacobian ring compute the primitive Hodge cohomology if the degree is not prime to the characteristic. So we don't know how to compute this thing. I mean, let's see. Actually, this computation for the quadric, there was an earlier method which works for sort of generalized Fermat hypersurfaces. Things of the form summation AI xi to the m equals 0, where m is anything. And even then, I mean, this uses sort of you take a Lefschetz pencil for this thing, and it's easy to see where it degenerates, where you get singularities, and there's like a Riemann-Hurwitz formula for that. But even then, I think I needed the degree to be prime to the characteristic. And if it's not one of these Fermat of course, if m is 2 and the characteristic is 2, it's no longer smooth. I don't know how to make the computation if it's not diagonalized, not a generalized Fermat hypersurface. So, it's just something to do. Could you repeat that? Yes. Yeah. Over every quadratic extension, in fact, over this quadric x² plus y², x1² plus x2² plus x3² has a rational point over every quadratic extension of Q2. And, then you get a formula for, well, I didn't try too hard because it's more fun not to be able to do it, right? You can just write it down. Why do you need all this machinery? So, yeah, give it a try. I'd be happy to hear it. I mean, it can't be so obvious because for R, there aren't any, right? But there are for C. So just having 1 over C doesn't give you 1 over R. So, might work, I don't know.
More questions? So your last bit, I mean, the end of boils down to
Hey, what's it?
I mean, in the end, everything boils down to really.
Yeah, exactly. Yeah. Well, you can always hope. But I don't know. I hope not. I don't know. It's possible. I really don't know. It's subtle because, again, it's, you have this group here. It's not just the values, it's the group generated by the values. So, I mean, what goes into this thing is you have this quadratic form, like in this case, x² plus y² plus z². That's the quadratic form. And that's not a Pfister form, but it's a Pfister neighbor. If you have a Pfister form, the set of values is already a group. So, and it's sort of comparing what happens with a Pfister form and its Pfister neighbor, which is in it, and this group is the group of values of the associated Pfister form for the Pfister neighbor. It's something, you have a Pfister form, it's a particular kind of quadratic form, and then you just eliminate a lot of the variables, but not too many. Pfister form has rank 2 to the m. And if it's a subform of the Pfister form of rank bigger than 2 to the m minus 1, that's a Pfister neighbor. Okay, I didn't know that. Yeah. Thank you very much.